Today I want to explain you the workflow for cable state bridges force shape optimization. If we have a cable state bridge, we first make a force finding for the final system. That means we want to know the cable forces that are necessary that for traffic opening we have a good bending moment in our system. There is a first example, CSM 21, in the CSM optimization folder. If we work on the final system, when we start with an analysis, we first estimate our pre-stress in the cables. Then we get, maybe under dead load and additional dead load, a deflection, and we get an unbalanced bending moment. Of course, we do not want this bending moment. The deflection is not so important. We will come to the precamber later on. Now, the optimization starts with analyzing single load cases for each cable stressing. That are scalable load cases. We stress the first cable in one load case, the second and the third. And then the back cables as a last option. These load cases are all calculated on the final system. Of course, this is only possible in a linear run, because here the brown cables get compression in this analysis, but this is not a problem now. We have 8 scalable load cases, pre-stress load cases. So we can wish 8 targets. Here we wish the target of the deformation Vz equals 0, because when the deformation is 0 here at these points, we automatically get a well-balanced bending moment in the superstructure. And the backstay cables, we can wish us the deformation Ux equals 0 on the top. This we can input in the CSM optimization tool, where we say we have 8 scalable variable load cases that have been analyzed all on the final system, and we have 7 targets UZ and 1 target UX, and the target shall be reached at the load case here 1, where we had dead load and additional dead load. The CSM can automatically build an equation system of these 8 load cases, because every load case pre-stress gets a deformation in all other loads, so we have a full occupied equation system. CSM solves this equation system and gets the factor that CSM calculated. If we run the analysis including these factors, we get this result. The deformation is really 0 at these points, and the bending moment is well balanced. So we have now a target for the final system with a very good bending moment, and of course we get the cable forces in every stage, in every element. If we have construction stages, it is not so easy. We cannot calculate the single scalable load cases at the final system. We calculate the load cases in the construction stages. Therefore we have a nice example, CSM 23. We start with the first segment, then we stress the first segment, only in this example. Then we stress the cable on the left. We build the next segment, stress it, cable on the left. Next segment, stress it, cable on the left. And then we add here the next element and the corresponding support. And we add the element here on the right with the corresponding support. Control cantilever 2, tangential building. This was the first estimated pre-stress. We just made an estimation for the pre-stress, and we see that we get this deformation, and we get these cable forces and this bending moment. Now it is best to use a bending moment as a target. We want to optimize the bending moment because the deformation is not possible if we have a construction stage analysis. The target that we want is in the superstructure. Here, good bending moments, also here, and no bending moment in the tower. Also here we have 8 targets. Of course it can be also 7 or 9 or 20. And if we have 8 targets, this requires 8 scalable load cases. Now we have 6 pre-stressing load cases available, and we need 2 more. Now what can we do? I choose here a support lowering and a support lowering here, because if we cannot use these cable pre-stress to optimize this bending moment, because in the construction stages where we stress these cables, this element is not active, and we have no effect of a cable pre-stress on this element. So here the best way to change the bending moment in this element is a support lowering here, and if we want to optimize the bending moment here, we can use a support lowering here. We could also use the ballast, but here I used the support lowering because it is more clear to choose a load case that really affects the bending moment here. The input in the CSM equation run is best to define the scalable load case here on the left, and then the effect that can be reached with this. If we stress the first cable, that is this cable, we can best optimize the bending moment here, because if we stress it, we directly affect this bending moment. And also here for the last support lowering can affect best the bending moment here at this position. If we input these targets in our equation run, CSM can also build an equation system, solves it, and if we run now the analysis new with these new factors of pre-stress and support settlement, we get this bending moment in the first run. Because it is a linear system that we calculate here, already in the first run we get the first correct bending moment in our superstructure. Now overview, what have we done? We have made a first straightforward analysis with estimated pre-stress. We got this bending moment and a bad deflection. With the optimization of the bending moment, we now have a very good bending moment. If we see to the result of the deformation after the construction stages, we see that the bridge goes down a little bit on the right. But this is not a problem. Don't care on such a deformation, because we just have to precamber our bridge. That means in the beginning build up a little bit the cantilever, and if we build up the cantilever a little bit in the beginning, we will get also a straight bridge without changing the bending moment. Here I have used a simple linear precamber. That means we get the good bending moment as well, and on traffic opening our bridge is straight. There is another video showing the precamber technique in detail. Now in the next example I show a nonlinear construction stage. If we have cables with a cable sagging, we have nonlinear effects, and we can also optimize this with CSM. CSM 29 is a good example for this. We start with a system. In the first stage we activate the first element and the first cable, only dead load. Then as a scalable load case we can stress the cable or shorten the cable. In the next step we add the next segment and the next cable dead load, and we stress or shorten the next cable. Then we add additional dead load and we end up in this system for the first estimated run. Now it is always clever to insert here a stage where we only activate the beam without dead load, because maybe you know, if we insert a segment, also shown in the precamber video, if we insert a segment stress-free, we can later on see the precamber of this element very clear. Now in our CSM optimization we again choose the bending moment as a target, so we want a good bending moment here at the start and a good bending moment at this position. If we start our analysis with the first estimated CSM, we get other values, maybe here only 400. The CSM input is now quite clear. We have two scalable load cases of the pre-stress and two targets of the bending moment. Now we must make an iteration, because it is a nonlinear system. The program makes here 7 iterations, and we see after 7 iterations we really reach our target 950 and 750 as a bending moment in our beam element, and we get these pre-stress factors that are necessary. This is now the result after the optimization. We have the bending moment that we wanted, and the deformation at traffic opening is also straight, because we have also added a precamber in the analysis. We have a cable sagging, that was the nonlinear effect in this example. It is very important that from this result we now get the stress-free length, the unstressed length of our cables. Just in WinGraph we see that at the last stage we can plot the unstressed length, and this is the stress-free fabrication form. So with 66.987 meters we have to fabricate our cable. We have also other stage analysis possible here. We can have additional help pylons on an arc bridge again, and again if you have an analysis where the both cantilevers do not come together in the first analysis, this is never a problem, because the precamber is very cheap, and the precamber does not change the forces or bending moments in your system. You just can optimize the deformation with the precamber. Very easy and cheap. So if in your analysis the two cantilevers do not fit together, it is really not a problem. Don't care about this deformation. you can always make a precamber for this, and the precamber will not change the forces in your elements in a linear analysis. So if you have a stage construction analysis, please only look to the bending moments that you want to achieve here for the arc in the final system at traffic opening. So this was an overview over the force and shape optimization on cable stayed bridges. Thank you for your attention.